Thanks, Denis. Thanks for the organizers for inviting me to give this talk. So we're going to talk about semi-toric SYZ fibration. That's basically a term essentially for the things that Melissa was talking about, but maybe if you know some SYZ literature, usually people remove an anti-canonical divisor. So that's basically the main example, the main class of examples for this. But I want to describe it a little more in more detail to emphasize the aspects of the symplectic geometry that are relevant to the talk. So the setup is, so we have M is M, and I will assume n less than or equal to 3. Return is 0, and we have and there's and then we have an n minus 1 dimensional torus which acts on M in a Hamiltonian way. So it has a moment map. Mu, which goes from M to Rn minus 1, which is sorry, GD plus. So we have some kind of identification of a group with Tn minus 1, and then the algebra is Rn minus 1. And then we pick an nth Hamiltonian, so I call it HB, and so it's just a function from M to R, and we require it to take it together, so we have this map mu, and then we have HB, so take it together we have a map from M, so let's denote this by L. So L, which I define to be the pair mu HB, which is a function from M to Rm. So I want this to define an SYZ fibration. And what this means is that it means that first of all we have an SYZ fibration. So what this means is first of all is that this function HB commutes with mu. So together, and it's generically independent of mu. So basically this means that the fibers. So for a generic point x and Rn, we have this is a Groman torus with massive plus 0, and well, and there's some kind of additional requirement about how these like the singularities have to be. So I won't write down now. I will in the examples. I will just say that the singularities have to be admissible in some sense. And there will also come one more technical condition on what on the singularities. But basically, this is the setting. The setting is where you have an n minus 1 torus action, and you complete it to a Lagrangian torus fibration by adding an nth torus. So the nth torus generally it does not generate. It generates an R action, but it does not generate an S1 action. So examples. So we have the trivial example, which I mentioned it just because it's covered by the discussion. So we take the potential model of the n torus, which we think of as identified with Rn times the torus, and then the moment map will just be the. So let's say we have so the moment map of say x1 xn, theta 1, theta n, I will just take it to be just xn minus 1, and in this case our third Hamiltonian will just be the last coordinate. So that's like a trivial case, which is not very interesting. Then, okay, so the second case is to take Cn and remove the product of so z1 to zn. So remove the set where zn with the product of all the coordinates is equal to lambda, where lambda is some complex number which is non-zero. This is the setting for mirror symmetry and complement of an technological divisor. The Nice paper. So, and then in this case we have the moment map, which is I'm writing as a vector. So it's z1 squared minus zn squared, zn minus 1 squared, zn squared. This, of course, like we're just talking about the torus, which acts by theta n minus 1, acts like by composing with this matrix E to the theta 1 minus I theta m. So this is already a non-trivial setting. Okay, so that's, and this should be thought of, so I said something, that we assume something about singularity. So this basically gives a local model for singularities. So near a singular point, at least a singular vertex, we have this, we have the same, the neighborhood of a singular point, of a critical point is symplectomorphic to the neighborhood of 0 in this picture, of like the most general term. Okay, so before I proceed, I will say just a non-example. So we are dealing with the same kind of setting that Melissa was talking about, but still, I have to say, if you just take a toric labial, that's not an example. So I mean, if you take a toric labial with, like, you just take this torus action, that's not, that's the 5, so it also has, like, it has a moment map, and we have torus fibers. So these are not, they don't have Maslov class 0. So it's not an SYZ fibration, and incidentally, I would say that to properly define the wrapped Fukaya category, then of this setting, then it's true. Unless you add some kind of potential, which is something more. So that's a non-example. And then, but from these toric labial, we do get a family of examples. So, which these are the examples that we will be building. So if we take, if x is toric labial, then this gives a, first of all, gives a volume form, a non-vanishing volume form, omega. And then there is a subtorus, which Melissa was mentioning, which preserves this volume form. So it's a Tn minus 1 dimensional torus, so which is defined by the condition that it preserves omega. So then, okay, so we take the moment map. So mu will be the moment map I was just writing mu equals mu g. It's the moment map of this of this torus action, and then, okay, so if we pick, so that's one thing. Now another thing. So first of all, so I said the toric labial gives you a volume form, and it gives also a holomorphic function, which goes from x to and which is G invariant. This canonical global function, and then so I will take so my manifold. So I will take M will be X after I remove the pre-image of a regular value. So you should think of this function as a generalization of just the product of coordinates for toric LBL, and then I can remove a regular value. And since F is preserved by G, the moment map still generates a semi-toric action. So semi-toric just means that we have an action which is one dimension less. And then I just take the Hamiltonian. I will take to be the logarithm of the absolute value of F minus lambda. And then this, you can see just by these definitions that this commutes with mu. And it commutes with mu and is generically independent of mu. So it defines. So this does define a Lagrange torus fibration. And basically for the low dimensional orbits of so all the singular points in HB occur where you have these the lower dimensional orbits of this torus G. So you have some kind of associated, so like this the locus of singularities. Let me just write. So delta will denote just the set of singular values of L, where I reminded that L is just you take together HB. So it's the singular values of L inside Rn. So it's dimension 2. So if we think of the dimension 3, so in general we get some kind of some kind of graph, such that over so the generic so this we think of this as some kind of graph which lives in Rn, in this case like in R3. So like for a generic point in R3 we have a torus, and then for points on these legs we get some like a product of some kind of, we get a certain immersed torus which is a product of this pinch torus with an S1, and then we have something more singular here, and what I was saying before is like that. Like in this neighborhood, a neighborhood of these singularities looks like locally like a neighborhood of 0 in here. And anyhow, and then so this is just some kind of graph which lives in R, and so it doesn't have like there isn't like R has an integral affine structure, but this is not in any way an integral. This is not like this doesn't consist of straight lines inside Rn because. But we can project. So if we forget the nth coordinate, we get something which lives in just in Rn minus 1, which we think of as the Lie algebra of this torus. So that has some kind of so once we project, we get some kind of graph with integral slopes. So it's some kind of rational graph. Anyhow, and. So yeah, so like our assumption is that so this will be the main class of examples, and the assumption after forgetting the nth coordinate, delta is a smooth tropical curve. Okay, so this. Okay, So this is our setup. And okay, so this has been studied, of course, this setup has been studied extensively. And so most relevant to what I want to talk about is the SYZ discussion. So
I'm sorry, the interior of the triangle is part of delta?
no, just the, like delta is just these points, the codimension to so from the SYZ point of view,
So just to make sure here, n is free in,
N
otherwise
is
you wouldn't
free,
say
yes,
curve.
yes.
Yes. Okay.
I'm being, so for this talk, like in general, n is 3 or 2, but some, like most of what I say is probably true when n is general. So that's why I'm keeping the n.
Sure. But then it would be a smooth tropical hypersurface.
Yes, yes.
Okay.
So, yeah, so from the SYZ point of view, when we have a SYZ fibration, we can talk about an SYZ mirror. So it has been studied. So there were two groups, like and that's one group of people, and this a separate paper by Chan, Jung. They studied the SYZ mirror of this, and what they found is that so if M is as above, then M check, there's an SYZ mirror, and M check is subset. So maybe I should use Melissa's notation. So I'm sorry, my habit is opposite to Melissa's notation. Maybe I'll write this. So there is some mirror curve. And I will drop the Kähler parameter from the notation, though it definitely should be there. So they found that this is the mirror. Morally, we have this as a subset in C2 times C star to the power of -1. So like you start with the manifold M, you apply SYZ mirror symmetry, and then you get this dual manifold. But yeah, but maybe more like from my point of view, more correctly, it's something which lies in some Novi covering. Let me like later we will everything is over some Novi covering. Let me not write that down now. So this is yeah, and this is some kind of Laurent polynomial, which well, so its Newton polygon is basically as Melissa describes, it's a dual graph to the discriminant locus, and well, the relation somehow is that. So this is so this is some kind of basically we should think of as so we can draw some kind of amoeba, which is which combinatorially looks like the discriminant locus, and then we have some conic fibration which degenerates over a hypersurface whose amoeba looks like the discriminant locus. So that's the statement of SYZ mirror symmetry. Okay. So, and there's some kind of nice switching here. So on this side we have, so we have like a two-dimensional base, and we have one-dimensional fibers, on which there is like an S1 action. And on this side, the picture that we have is essentially where we have a two-dimensional torus action, and And then we have this third Hamiltonian, this function f, which this global function f, which we may think of as a function to C star. I'll just write it as a line. And so what we see is that so mirror symmetry sort of swaps, so it takes a torus action to a pair of global invariant functions, and it takes a global invariant function to an S1 action. So like under mirror symmetry, an action turns into an invariant function. That's just an aside. So anyhow, so what is the question I want to address? So the question is, what is...
So I didn't understand that particular discussion in any way, shape, or form.
What?
I understood essentially nothing that happened on that board, so maybe you could revisit it briefly. There's no H on the left-hand side. I have no idea what the fibers of the map M are. Is there any kind of genericity about new?
Yeah. Sorry. Okay. Let me. Okay. So
I'm just
so for me, M you should think of as an example 3, which I wrote here. This M.
Okay.
And there's a function f.
Which is valued in C, not C star over there.
Well, after we remove, since M is,
okay.
So it is valued in C star.
Okay.
And then there is a torus, which acts basically on the fibers of this map. Okay. And then I was saying, okay, so there is some H. This H is related, so this H is like a Laurent polynomial, so it has, so you could say describes some surface in C star to the n, hypersurface of C star to the n minus 1. And that hypersurface is related to discriminant locus in that the amoeba looks like the discriminant locus. Is that, sorry. Anyhow, so yeah, what do we want? So we have this M, and I want to have the wrapped Fukaya. Okay, so why do I want this? Because like homological symmetry says that if you have, so says that the
Sorry, can you say of which one? Of M? Or?
of M. I'm just looking at M, and I want to know what is its wrapped Fukaya. And then there should be something here. And as far as I know, it's not been like it has not been like this kind of setup has not been constructed. Like maybe for this particular case, yes, but for general toric labial, as far as I know, it's not been done. And yeah, what is the? Sorry, you have a question?
Sorry, is your X M or M check?
Oh, sorry. Yeah.
X is M check.
Okay, and so what is the problem? So in general, people work with the Fukaya category for things which are exact or which are conical at infinity. So in general, this is not generally conical at infinity. So basically, there's a question of like technically, you'd say there's a question of like how do you handle things like compactness, but like the non-technical question is like, well, basically, what exactly do you need to do? How to wrap? When we have a non-compact manifold, well, we know that like the Floer homology depends usually on the growth rate at infinity, and we like to have some kind of natural way of defining some rate of growth for which which would be natural from the point of view of SYZ mirror symmetry.
Are Lagrangians in M going to be non-compact in both base and fiber?
Yes, I will allow Lagrangian, like a section, like I want to compute the Lagrangian section. Or, an average alpha brains, that Melissa was talking about. Right? So I just recently found that there's a paper by Kontsevich Seidelman, which suggests an idea which is similar. So I'll write that down in a minute. But let me first let me describe the basic heuristic. So I'm just to pose to you another question, and that is when you look at this formula for the mirror, you see that you have something which is given it's a finally generated algebra. It's given by a polynomial relation. Now, at least if you the SYZ literature is usually you get some kind of rigid analytic space. So SYZ. So I think it was so you have a cubed, and you have this was done in detail. Two, and you have the series of papers by Mohammed. So usually they give constructions in the rigid analytic rigid analytic world. So the question is the fact that we get something here which is algebraic, is this a coincidence, or is there some intrinsic reason which comes from the symplectic geometry? So where does the algebraism come from? And then, so the guiding principle is that so we just take the heuristic from the simplest case. So we look at T star S1, and then so we have this cylinder, and we fix some Hamiltonian, which is linear at infinity, and 0 on some compact set, and then we know that we can define a symplectic cohomology of the setting, and it gives, so we can define it by just taking a direct limit. So let's h as this function. We take a direct limit when a goes to infinity, and that happens to be, when you calculate it, so let's say this is a pseudo definition, and then when you calculate, you get Laurent polynomials. So again, you get something which is so you get some algebra, polynomial relations. And well, basically you could think of so basically there's a filtration. So the slope at infinity is, or filtration by slope corresponds to filtration by essentially by the order of the. So there's a specific there's a specific rate of growth in this story, which defines some kind of filtration by order of pole. So essentially we need to have so if we want to define rapid, we have to have some kind of notion of linear at infinity, which corresponds to where the like say the rate of growth, so kind of with the slope at infinity would correspond to basically to some kind of like pole at infinity or some notion of algebraic complexity. So yeah, so the way so generalization to our setting. So we have this SYZ fibration. So it gives rise to a so integral Fn structure. So there's some kind of integral Fn structure, which let me denote it by A. So an integral Fn structure with singularities. On Rn, which is not like, this is not the standard integral Fn structure that you have in Rn. So that in some kind of, in a two-dimensional setting, so say, so this is R2, and here we have a singularity, then if we remove something, then we get some kind of so we have like affine coordinates on this set, but when we go around, there's some kind of monodromy. So it's not so because of the singularity, we can't extend the integral affine structure across this array that we remove. But so basically, what we have is we have a cover by sets like this. So we can say in this case we can cover it by two sets. One will remove this ray, one will remove this ray, and then we have like every point except like there's a singular point, and then on the complement of the singular points we have locally we have an integral affine structure. So we want to use wrapping by the integral affine structure. So to formulate this precisely, I should so we have an arbitrary integral affine structure won't necessarily allow you to define what you mean by linear at infinity because we have the presence of these singularities, which are not like in R2, it's a compact set. But if you're in R3, then the singularities where the integral affine structure is not defined is basically the discriminant locus, which I wrote down earlier. So is this reachable, this part of the board? And yeah, that discriminant locus is not a compact set. So we have to assume some kind of well-behavedness, which I won't, which I don't want to describe, but I want to somehow make some technical point. So I'm saying if this is sufficiently well behaved, then the integral affine structure will give an equivalence class of Riemannian metrics on the base on Rn. Which is characterized by A is, so the integral affine structure gives you integral coordinates. So in the sense that these integral affine coordinates are Lipschitz. whenever you take some kind of uniform neighborhood between away from delta. Sorry, yeah, away from delta. So this gives you some kind of class of Riemann metric, and this which in particular defines a set of functions, which I just write as a class of Riemann metrics. Just any one of them are called G, and then this gives there's Lipschitz functions on the base. And of course, if you have functions on the base, you have a collection of functions on, which I will denote by H sub L. So this is these would be functions on M, essentially compositions of H with the fibration, such that H is Lipschitz. So this is a subset in, this is a subset in a set of functions on, it's just functions on M. And once you have a set of functions, it's not just a set of functions, it's a semi-group. You can add such function. And such a construction, whenever you have a set of Hamiltonians which is closed with respect to addition on a sufficiently well-behaved symplectic manifold, this gives rise to a ring. So this is like a result in the paper of mine about the Floer-Theory manifold. So which essentially you should think of as just taking the limit of the Floer homologies over these Hamiltonians. But the upshot is that, well, why do I care about these Lipschitz functions? So the upshot is so HL has, or let me say, the set of Lipschitz functions. Has so it has a confinal sequence HI such that the differential of HI is non-integral outside a compact set. Now, the flow of any such Hamiltonian is it flows in the fibers of your torus fibration. So if you have something which is non-integral, then the Floer homology of HI then is necessarily finite dimensional. And this gives you a filtration on symplectic homology, which is respected by the product. So by the pair of pants product. Because basically you can write the symplectic homology as the here. So the symplectic homology, you can just take it as direct limit of these Hamiltonians. So you can just write so it's just then the Fleur product essentially goes from so if we have I and J, then the pair of Brent's product always maps into sorry, this is I, this is J. So it maps into some K where HK is greater than. So we have this filtration. So this automatically so relations are given by polynomials. So like this doesn't tell you that it's finally generated. So but it somehow looks like the this construction is the one which this is the kind of Floer theoretic construction which would give an algebraic structure. And I should say that similar ideas, I think, so a similar idea was suggested in a paper. So instead of server one, something about wall crossing. Something like this in the so anyhow, okay, so this is the closed string. So let me very briefly say, I spent a lot of time in the closed string, so the open string will just go through very fast and at least formulate what mirror symmetry says here. So this is closed string wrapping. So for open string wrapping, we also need to choose a section. So okay, so pick a Lagrangian section sigma. And then relative to this sigma, we can have, I will like, putatively, I will say that the objects of the Fukaya category, not in a completely correct way, is Lagrangians such that, so Lagrangians given by a co-normal construction outside a compact set. I'll explain what this means. So you have we have this integral f as structure. So we can take so we can take some submanifold which has rational slopes, and then given this Lagrangian section, that so let's say this is the torus fiber, and then the Lagrangian section picks some point in the torus fiber over a point in the manifold, and then just using the symplectic form, we get some kind of complementary. So we get a submanifold in the torus, which complements this the tangent space to the say to the section, and then we get. So if it has rational slopes, we will get some subtorus, which so basically we get Lagrangians which are basically certain tori which are fibered over rational so manifolds outside of the compact set. And then, of course, examples are so sections. So basically, if I'm very rigid about it, it's just sigma. So sigma. And then torus fibers. And then also there's Adenauer Rafa brains that Melissa was talking about. So this gives me the kind of objects in the category, and well, okay. So this is not completely correct. So, well, when I want to define morphisms, I run into trouble because of this bone. So there are two ways to go about this. So one way is to use f of q to say that objects are pairs, Lagrangians and bounding cochains. But I use this in a slightly different way, which maybe is not philosophically correct, but I think it also has, it throws light. And at least it's good enough for a section, because sections are basically don't really have, a more Cartan, they don't have a modular space of, like the space of more Cartan elements is zero dimensional. So anyhow, so yeah, so for morphisms, I'll just say that, so if we are in this, at least we are in this semi-toric SYZ setting, then, which remembers, we said we had like a global torus action. It's a global, so n-1 global action coordinates. So dually we have a global angle coordinate theta n, and then we can use this. So it's just a map from M to S1, and such that d theta n is a generator of the cohomology, of the first cohomology. So we have this global angle coordinate, and we also had that so we had that function HB. So that third, the nth Hamiltonian. So we have a function f. So we have this global function. Of course, you could say that I'm just going like moving around my tail because like, it's just this function f, which is written up there. But there's a reason for doing, like I want to give it a symplectic description of this function. But anyway, you just think of it as just that function, which is up there, and then there exists like there exists almost complex structures J such that f is J homomorphic, and such that the critical points of L are contained in a fiber of F. So I will just restrict. So once I fix the point of doing it this way is that like that function f is like a particular homomorphic function, but in fact like there's a lot of flexibility in like this function h. There's nothing canonical about this function h. We can move it around. So like it's relevant for understanding wall crossing, but I think I don't have time to go into this. So anyhow, so once we have this construction, I impose that so on my Lagrangian I will impose the condition that so I will so L is admissible if, in addition to having this conormal construction, it satisfies that 1 and L does not go through the pre-image of this singular fiber. So particular unfortunately, like the Aganagich Waffa trains are not covered in this definition. So a proper definition would require using the FOQ formalism. So that's one. And the other is that if we push down the Lagrangian, it does not wind around so if this is the singular point and we push down the Lagrangian, we don't want it to look like this. And then whenever we for Floer theoretic operation, we want to find whatever differential or.
So you don't want it to wind around the singularity, or you don't want to wind
Sorry?
around? You don't want it to wind around the fiber that you deleted, right?
I don't want it to wind around the singular points.
The singular points.
Sorry. I don't want it to wind around, like there's a function f, so it's a
Yes,
matrix.
and you deleted a fiber there, you don't want to wind around that fiber, right?
Yeah.
So which one is that again? The singular one or the removed one that you don't wind
This
up?
is, the singular one, not the removed one.
Okay.
The singular one, not the removed one. So, yeah, the only reason why I wrote f as a function to C and not to C star is so that I can write this. So yeah, like f, I think of it as a function to C, so there's no rule, like, yeah. Anyhow,
And you assume that there is only one singularity of your function, or only one singular value.
no, I'm saying that the critical points, so the function f is such
Okay.
that all the critical points of the Lagrangians
I missed that.
lie inside a fiber. And then, like, any disk has to meet these critical points, and once it meets one of these, it either must be contained in a fiber of f. That's like a property of geomorphic functions. So if you have such a function, then either you have to be contained in a fiber, or you have to wind around it. Like, that's just the nature of functions. Like, you compose with this function f, you get a function in C, and so either it's a constant function, or it winds around non-trivially. So,
Wait, sorry. The assumption was what for that statement?
The world is empty, L intercept everything was zero.
say if you have like if you have a function, you have a symplectic level, you have a function. Sorry, you have a geomorphic function f. Then any geomorphic disk with boundary, which intersects the fiber of that function, is either contained in the fiber or winds around non-trivially. Then you just deduce by composing.
Yeah, okay.
Let me just raise this more. I'm running out of time. So anyhow, so for Floer theoretic operations required. So say we have some kind of closed open operation. So we require, and then there's some almost complex structure. So require, and usually we have to allow the almost complex structure to vary arbitrarily on the domain, but we require that JZ is restricted to, so let's call this sigma. So restricted to the boundary of sigma, it should be this J from that pair. And then let me, so I still have 5 minutes, I believe, because we started 5 minutes late. So at least formulate the theorem. So yeah, so to formulate this theorem, there's just one last ingredient. So I mentioned this global angle coordinate. So this, which I said represents some kind of generator in homology. So it defines an x degrading on orbit allow ourselves to talk about it as bi-graded. Like the extra grading is by how much, like by the degree of theta n, which you could say is how much a periodic orbit winds around the removed fiber. So, so we get this bi-grading, etc. And this, like, and just for topological reasons, the product always has to respect this gradient. Like if you have a pair of bands, then the degree of theta on the output must be the sum of the degrees of the input. So we get this extra grading, and now we have a theorem which is currently still in progress. And okay, so the statement is so a sequence of statements which give homological mirror symmetry. So the statements are as follows. So first of all, zero symplectic homology of M coincides with the RAF homology of a section. That's true even under quite general conditions. Then, okay, then the zeroth. So we look at the 0, 0 part. We get the Novikov ring with generators. Like the group algebra of the group which is acting, which the n-1 group, which is the same as thinking of this as the so picking a basis, it's just Laurent polynomials. And so you should think of it. So sorry, I'll just first write on the statements that I'll comment. And then, so that's the 0, 0 part, and then the 0 part is just given by adding to the 0, 0 part two variables, x and y, together with the relation x, y equals some element, which must lie. Okay, and then 4 is that this G is like the mirror curve that Melissa was writing down before, so it's this. Let's write it as like this is the Hori-Vafa standard mirror that we've been talking about. And finally, 5 is if we take the open-closed map, which I think, like, so we just take the Hoffman homology of this of sigma. That we take the map to the symplectic homology. It hits the unit, which is this is the generation criterion. Of SYZ. So this and so in summary we have that the wrapped Fukaya category of like the bounded derived category is the bounded derived category of coherent sheaves on say spec of the Floer homology of the Lagrange section. Which is just like the ground derived, which is just the Horivafa. Okay, so that's the. So I think I'll stop here.
Thank you. Dmitry.
The all known examples of this setting compactified to like Farner varieties.
Again,
The
sorry.
all examples we know of these M's compactified to compact panel.
No,
And
of course not.
But,
Toric Calabia also.
Sorry, come on, yeah. Right.
So for your fifth cycle, so your open closed map is mapped to symmetrical morphic associated.
Yeah, yeah.
But why does this imply is a fact that?
What?
I mean,
Yeah, this implies that whenever you have so this is like a theorem by Mohammed, which says that when you have you take the option homology of some collections of ranges, and
but you already computed HWC error. Why do you know that? So the raptor local.
like the I had, yeah, maybe I should say that was automatically zero. These are all the chords have degree zero. So yeah. Yes.
So why do you choose
No, but he says there is more functions.
Oh, okay. Why did I so? Yeah. So there is basically a technical reason. Like I'm relying like the way I'm saying this, like I'm saying that like the symplectic theorems are not assuming some particular construction, and then like I'm using normal forms to like reconstruct, like say these functions f, these almost complex structures, and then
There's number 3 in U.
just like the results in the literature talk about up to n equals 3. Like results in the literature about normal forms,
Yeah.
singular, from Lagrangian torus fibrations singularities, like the papers by Matesi and Castaneda, they somehow link to up to 3. That's the main reason. But maybe there might. That's the main reason. Well, there is also like the way I compute this is also
I'm not sure. It's
there's also one more.
Maybe a step, item 4 maybe, where the technicalities come up in...
Yeah, like to get this G, like I believe in your paper you did this in quite, like I believe there's a way, so
So
there
we
are two
state
ways
it in
of-
all dimensions, but we are going to rely, that part is not quite written up, and we rely
No,
on
but it's
some
like-
fancy technology for...
but I saw like in the SYZ paper, isn't this written for arbitrary dimension?
Yeah, up to unspecified correction terms.
Okay. So,
But the Chan Lao long papers give an enumerative interpretation of those by relating them to closed Gromov-Witten theory.
so if I rely on the SYZ, then I think I could assume this. Like all I need for the mirror symmetry is just to know that this defines something smooth.
Yeah, so I think you should be good in all n.
All that. But I'm just using something which does not rely on, I'm using something which relies on, I probably can be done by somehow relying on the SYZ construction and going from there, but that would require some kind of technical work, which I didn't do. I did some kind of a different approach, which I don't know if it generalizes to n greater than 3.
Okay. I think.
Yeah, I have it. So sometimes in the case of related to what I talked about earlier today, then you can see somehow the infinity of this toric manifold kind of has an asymptotic contact boundary. And in this contact boundary, somehow these Lagrangians defines in the Lagrangians.
When you say asymptotic just a question, you mean like if I look at the complement of a large enough compact set,
So
the boundary is actually contact, or you're just saying some?
Yeah, I mean that there are these sort of typical. So, for example, for the conifold that I was talking, this whole conifold, you have one Kelly parameter. You go very, very far.
I see. So like when you
It looks
collapse
like,
it, like
it looks like
you
unit cotangent bound of S3. And I don't know in what generality you can define this asymptotic contact boundary, but I imagine you can sometimes, and then your Lagrangians will define the Schwangians out here.
Okay.
In this first case, what is very often the case is that if you take the Schwangian DGA, kind of this upside down Floer cohomology, you don't need an Hamiltonian and things like that to define it. When you take the Schwangian DGA, then the H appears as the augmentation variety of sufficient dimension, and then it's manifestly algebraic. I mean, it's somehow.
Okay.
Do you think this?
I don't know. I don't think of it that way, but
Do you know how to define your SH without Hamilton? Sometimes?
no, I didn't think of. No, but I hear what you're saying. Like you're saying.
But the point is that sometimes there are honestly kind of holomorphic curves out of things, which is
Okay.
no.
I just don't. I'm not just not familiar with it.
No, okay.
I don't know that much about it.
Geometrically, can you say why the conic bundle structure of these particular variables x and y appear?
Yeah.
They-
Yeah, that's a good question. So geometrically, so if you think first of all of the case where there are no singularities, right? So think about T star S1. Then the relation is just like you could say that you have so you have this relation is actually xy equals 1, and it's just like a topological thing because you like just by looking at the pair of pairs, you must have that the sum of the winding numbers of the inputs equals the
Maybe
one.
what you didn't quite
So,
say
so
is,
actually that automatically gives this.
maybe what you didn't quite say is x is the chord that wraps the orbit that goes once around one end, and y is at the other.
I see. X and y are coming from the base, and
Yes.
they don't product to one because of the presence of
Because of the
singularity.
singular fiber in the middle.
Yeah, they come from, so they wind around the missing fiber.
So, I guess like perhaps number 3 and 4 is saying that, and Dimitri's work is saying that this H doesn't hold like the wall crossing formula. Let's say if I want to shift from one of the fibers of your semi-toric system that does not enclose the singularity towards the other fiber that like does enclose the singularity. I'm still like in this setting where you only have like all singular fibers at one point.
Well, the wall crossing factor is exactly this polynomial H.
Yes, yes.
So
But
it's a
was
complex
this
wall.
already known before?
That's
Yeah.
essentially the SYZ construction.
Yeah. So
But
basically this picture.
even if there was like this kind of like weird kind of like singularities over there.
That's exactly what Chan Lao Lung and my paper with Mohammed
So actually, I just want to say a word. Like, there's a nice way in terms of this function. There's some kind of nice way of thinking of the wall crossing, which is okay. So basically, this function h it defines. So say this is a singularity, and then h defines like where h equals 0. It defines some kind of wall, but these are not in any way straight lines in the single FS structure. They have no intrinsic meaning. So basically, you can play around with h. So say you have a given torus fiber which lies at a point here, then you can take h to look like this, or you can take h to have a wall which looks like this, or to have a wall which looks like this, and then so the wall crossing occurs as you move this Hamiltonian from having this wall to this wall. There will be a certain point where it hits where this torus fiber becomes obstructed, and then so basically the wall crossing is this coordinate change on the space of bounding chains between when you do Floerology with this wall and when you do Floerology with this wall. But the point is that for the sake of like homological relativity, all this doesn't matter because like for Lagrangian sections you don't need bounding chains.
Okay. If there's no further questions, let's thank you all again.